All right, we're going to take a look at solving radical equations. A radical equation just means that it has a root in there, a square root, cube root, something like that. Now, the basic idea of solving an equation would be, we want to get x alone. So if I saw like 3x equals 12, I can divide both sides by 3. X would be 4. Some of our old two-step equations. 2x minus 1 is 7. I would add the 1 over. So 2x is 8. And then divide by 2x is 4. Right? So we've solved equations before. The idea of isolating an x, that's not new to us. What is new in this situation is there's a square root sitting here. So it doesn't look quite as easy as something like this. I need that square root out of the way. Right? So I need to get rid of that square root. Then I will have an equation that I have seen before. That doesn't mean that I'm going to have an easy equation every time, but it's definitely going to be something I've seen before. So to get rid of that square root, we're going to use the opposite operation. So the opposite of square rooting would be squaring. So what I want to do is square both sides. Now remember, our primary rule for solving equations is I can do anything I want as long as I do it to both sides. Okay, so I can square both sides. And what this is going to do is, if I square the square root, that's going to leave me with just what was inside, that 2x minus 3 in this case. And 4 squared is 16. Now that looks like a much more easier situation for me to work with. I'll add my 3. 2x then is 19, and then I can divide by 2. X would be 19 halves. Or, again, a decimal would be fine too. So that's the basic idea of what we're working with. We want to reverse out of that radical, out of that root by using the exponent. I need to do that to both sides. And the goal of that would be to produce something that might not always be easy, but it's definitely what I've worked with before. So I've seen that part before once I get to this step here. Right? So let's look at a few variations here. Let's say we have a square root, 3x plus 4, and then we'll put a minus 8 equals 2. Right? So instead of a square root equals a value, now I've got a minus 8 sitting in there. Anytime I want to get rid of the radical to produce something I've seen before, I need that radical to be alone. I need it to be isolated. So the first thing I want to do is add the 8 over. I need this, not a 2, that's a 3. I need this radical, the square root isolated, so I'd have the square root of 3x plus 4 is 10. Now that that square root's isolated, I can go back through my process of getting rid of that square root, which would be squaring both sides. And so when I square both sides, if I square this square root, that's 3x plus 4. And 10 squared would be 100. And now I've got, again, an equation I have seen before. Okay? So I can subtract my 4. 3x then is 96. Divide by 3, and that'll give me 32. So 3 does go into 96 32 times, so that would give me a value of 32 there. Slightly different look. Let's say 3x plus 5 to the 1/2 equals 3. Right? This is still a radical equation. It has a square root in it. This is just written with that rational exponent. So I need to remember a 1/2 power is really still a square root. So If you don't like dealing with the half power, the rational exponent, you can certainly rewrite it with the square root instead of the half power. It's more of just personal preference. If I don't rewrite it, that is fine, but I definitely need to remember, hey, wait a minute, that's a square root. That's going to tell me to square both sides to get rid of this. So square, square. 3x plus 5 then is 9. 3 squared is 9. So then I'll subtract my 5 over. That'll give me 3x is 4. And x then would be 4/3. So again, a little bit different look from the start with that rational exponent. Still meaning that we're dealing with a square root. That half power was a square root. And again, once I get rid of that square root, I'm back to something that's a little bit more familiar for me. Okay. Sometimes we'll see a different rational exponent up there. Let's say I had something like this. Let's go 5x minus 1 to the 1/3. So I've got a 1/3 rational exponent instead of 1/2. Okay. I still need to remember that a rational exponent is representing a root. Since it's a 1/3 power, this would be a cube root. So I can leave it like this and just realize that it's a cube root, or I can certainly rewrite it. Again, more personal preference there. Do you like seeing the root or the rational exponent better? Either way, the opposite of a cube root would be cubing something. So the opposite of square root would be squaring. The opposite of cube rooting would be cubing. So I want to cube both sides. So that would give me just the inside, 5x minus 1, and 4 cubed is 64. Right? Again, now I'm back to an equation that looks a little bit more familiar to me to solve. Add 1, 5x is 65. Divide by 5, we get 13. Right, so again, back to something familiar. I just needed the cube instead of square because I had a cube root instead of a square root. Right? Now, the rational exponent actually shows us why this idea is working, going with a square or say a cube. Just to kind of show you here on this last problem, if I left that as a 1/3 power, and to get rid of that 1/3 power, I'm going to cube, because it is a cube root. So if I were to cube both sides, power to power from your old exponent rules, that meant multiply. Well, 1/3 times 3 is 1. So that becomes 5x minus 1 to the first is 64, which is why that cube is taking out that cube root. It's really an exponent property, a power to a power. We're going to multiply 1/3 times 3 would give me that 1. Same idea if I look back at number 3 here. Why does this square just take out a square root? I can see it in a rational exponent form. So again, if I saw 2 go there, 2 times 1/2 is 1. So that's really 3x plus 5 to the first. That's why that root's going away. Right? So that opposite operation is what moves things around or changes that format. We can really see why that's working when we think of our old exponent rules. Just kind of giving you a little proof there as to why that power is taking out the root. Now, a couple of looks that kind of stump us from time to time. Something like this. I think this was 5. All right, 5. Let's go square root x minus 5 plus 10 equals 4. Well, initially, this doesn't look anything different from what I've seen so far. Okay? I did see one earlier believe it was number 2, where we had to isolate the radical. Same thing's happening here. I need to move that 10 over. Right? I need this square root all by itself, the radical by itself. So square root x minus 5, if I subtract 10, I get negative 6. If I have that square root equals a negative, this would be no solution. A square root can't equal a negative. Think about the old principal square roots. So for example, when you took the square root of 25, you've got 5. Took the square root of 49, you've got 7. Square root of 100, 10. Now you're never getting a negative there. Okay? So that's why I know a square root can't equal a negative. There's nothing I can put in for x that's going to make that work. Well, let's say you forget that. You don't catch it. Sometimes we just don't catch stuff when it happens. Right? So I would follow my same old process. I'm going to square. Square to get rid of the square root. Well, that will leave me just x minus 5 here. And that would give me a positive 36 because negative 36 squared is positive 36. And it looks pretty basic right here. I'm going to add my 5. X would be 41. But remember in the past, anytime you solved equations, it should work in the problem. So for example, this one that's still on the board, kind of back the way it was. I got an answer of 4/3. So that means if I were to put 4/3 back in for x, it better work. Well, let's check it. 4/3 times 3 is 4, plus 5 is 9. And then the square root of 9, hey, that's 3. That's working. Any of our solutions should work. Okay? Well, let's put 41 in. 41 minus 5 is 36. The square root of 36 is 6, plus 10 is not 4. Okay? So that cannot work. So we always want to make sure that we check our solutions. A lot of times we get in the habit of not checking because we're just so used to solving equations and we're confident in our work. Okay? But sometimes this kind of gets us right here. Right? That's going to be an automatic no solution. Square root cannot equal a negative. Or the other way around is just remember to check your answer at the end back in the original problem, and that won't work, right, for something like that. Right? So again, square root can't be negative. Okay. Here's a different look. Same process we're using. We're just getting a couple different looks there. So here, that had a negative. Let's say we had a square root equals a square root. So I've got square root 6x plus 5 equals square root 3x plus 11. Well, we've only seen one root so far. Most of them have been square roots. We had one cube root, but only one root in the problem. This one's got 2. Okay? Well, our focus has been make sure that the radical is isolated. Well, I've got 2 of them here, but at least they're both isolated. So I have them both alone. So that means I'm good to go through and get rid of those radicals. So I can still square both sides. Same process on both sides. The square is going to eliminate that square root. That'll give me 6x plus 5, 3x plus 11. And now it definitely looks like something I've done before. Okay? The look in the beginning was a little bit different. The roots were isolated. I'm able to get rid of those roots. So now I'm looking at something that, again, might not always be easy, but it's still something I've seen before and worked with before. Let's see, I'll subtract my 3x. See, 3x plus 5 is 11. Definitely starting to look a little better now. Subtract my 5. 3x is 6, and so then x is 2. And we can even use that idea of checking, because if that 2 doesn't work, it would be a no solution. But let's take a look here. 2. 6 times 2 is 12, plus 5 is 17, so this left side would be root 17. right side, 3 times 2 is 6, plus 11, 17, root 17. So root 17 equals root 17. Yeah, looks like that 2 works. Okay. So we've seen a radical equal a single value. We've seen a radical equal a radical. Okay. And again, these come out actually pretty good. Now we're going to look at a radical equals a binomial. I still need to make sure the square root of that radical is isolated. And so it is at the moment that square root 8x plus 1's all nice and alone, which means I can work to eliminate that square root. I know there's 2 terms on the right side, but don't change your process. We haven't been randomly just squaring everything. We've squared the left side, squared the right side. We had a cube root, we cubed the right side, cubed the left side. So we're doing the same thing to both sides. So when I square this, I'm going to square that square root, and then I'm squaring the entire x plus 2, that binomial. So this becomes my easy part here, just the 8x plus 1, same thing we've seen over and over. The right side, I've got to square out this binomial, and that's going to be x squared plus 4x plus 4. Just a reminder, if I'm not the best at squaring that quickly, when I see that x plus 2 squared, sometimes it's easier for us to just write it twice and then go through our multiplying. And there's where I'm getting the x squared plus 4x plus 4. Okay. Now, this is not giving me a linear equation like I've seen in the past. I now have a quadratic equation. And makes it a little bit tougher to solve, but we've still solved quadratic equations before. So a quadratic equation, I need it equal to 0 because I see that square. I know I'm going to have to factor. That's going to be my goal, is get it factored correctly. So that's 0, x squared. I'm going to move this 8x over. So minus 8x. That's going to give me a negative 4x. 4x minus 8x. And then 4 minus 1 is that positive 3. Okay. So again, not as easy as a linear equation. Still something I've worked with. I can get this factored. X minus minus 3 and 1 to give me that negative 4 in the middle. So then I'm solving my 2 individual pieces. Again, a little bit longer process with the quadratic. But still, that process should look familiar. Now let me check those solutions. Check this 3. 3 times 8 is 24, plus 1 is 25. Well, the square root of 25 is 5, and 3 plus 2 is 5. So that 3 is just fine. Let me check the 1. 8 times 1 is 8, plus 1 is 9. Square root of 9 is 3. And hey, 1 plus 2, hey, that's 3. So I've got 2 solutions here. Okay. So I'm checking both of them. They both end up working in the problem. If one of them did not work, I would exclude that solution and just keep the other one. But I need to make sure they're both going to work. Right? We're back into the original solution there. So the idea is solving radical equations. Get rid of that radical. Most of what we're going to see are square roots. I would square to get rid of the square root. If it was a cube root, I'd cube to get rid of the cube root. And then I would solve that resulting equation. Sometimes we get a nice, easy resulting equation. Sometimes we get one that may give us an extra step. And sometimes we get ones a little more involved. But again, I'm thinking of factoring because I see that square. But this still, the resulting equation would be something we did before.